The very best images that we have of the surface of Venus come from the Magellan spacecraft sent by NASA. And this was back in the 1990s. And they're not actually images. They are a radar scan of the surface of Venus. And they're not at a very high resolution. And the problem is that we can't see really the colors of the things that are down there on the surface. What's a lava flow? What is a volcano? What is a rock? What is what are the different chemical characteristics of the terrain? And so to really get good images of Venus, you have to get closer to the surface. You have to go below the cloud deck down to an altitude of about 45 kilometers before you can actually start to see with infrared and visible light. But trying to get down to that point is very difficult because of the intense conditions. So my guest today is Benjamin Hockman. He is a robotics technologist at NASA JPL, and he is one of the recent NIAC award winners for a Phase 1 grant called TOBIAS, the Tethered Observatory for Balloon-Based Imaging and Atmospheric Sampling. And the whole point of Ben's proposal is that you could have a balloon that floats higher at a more reasonable temperature, that sort of 55 kilometer altitude, and then it reels down a tether with a probe that can then be brought below the cloud deck to take those high resolution images of the surface of Venus. Now, of course, there are a lot of challenges in terms of temperature, in terms of the wind speeds, getting electricity down, and all of these will be explored as Ben continues with his NIAC grant. So enjoy this fascinating conversation with Benjamin Hockman. Ben, I've been doing a lot of interviews with people about Venus, and I'm getting a little obsessed with it right now. And I think, a lot of the conclusions that people are coming to is just how interesting that upper atmosphere of Venus is. And so, with your grant, you're looking at a tether system. Can you kind of explain how this might work?
Yeah. So, I didn't come from a Venus background, but also like you kind of have been exposed to all these crazy ideas for exploring Venus. And, even learned sort of late that the Russians did something like this back in the 80s with 2 balloons. So aerial exploration of Venus is not new for humanity, though NASA never had much success back when they were trying to explore Venus. So what we're envisioning is essentially a long-lived aerial platforms that would be essentially hosted by a balloon, helium-filled balloon that has actually 2 balloons, one inside of another, where it can pump helium between, and it does that so that it can vary its altitude and explore different heights in the atmosphere. And that's kind of a nice Goldilocks zone for exploring from a environment perspective, because the temperature and pressure are not too dissimilar from our own atmosphere on Earth. Of course, as you get lower and lower and closer to the surface, things just get much harder. The pressure goes up, the temperature climbs to, melting points of aluminum. So while the Holy Grail is to bring something like, the Mars rovers to Venus, we're just not quite there yet from an engineering standpoint and high temperature components. So I think the next frontier for exploration is this atmospheric platform. And so what our NIAC is explicitly focused on is sort of extending the reach of these balloons, which sort of have to live in the Goldilocks zone, down further towards the surface. And the key reason that's important is there's this really pesky cloud layer at around 47 to 52 kilometers in altitude. And once you get below that, you can see the surface much more clearly with your cameras.
Oh, really?
Yeah.
Huh.
So it's not just an atmospheric sampling mission, it's also an imaging mission. So the balloon kind of has to stay in this like 52 to 62 kilometer altitude band for safety. But it's occluded from seeing the surface, at least in the visible and IR spectrums that are interesting. Of course, satellites are imaging in radar, but scientists really want to see the surface in visible and IR to see all the volcanic activity down there too. So the idea is to suspend a platform, we're calling it a tow body, on a multi-kilometer long tether, a very thin tether, that would allow the balloon and the primary, what we're calling gondola, the host payload under the balloon, to stay up in that Goldilocks zone, while allowing the smaller platform with a camera and atmospheric sampling instruments to get down below that cloud layer and actually sample the whole profile. So that's what we're trying to develop.
Right. And, I think people are very familiar with this idea that, when you're at, say, 55 kilometers altitude on Venus, the temperature and the pressure are very Earth-like. You've got the pesky sulfuric acid that's flying around, but a little Teflon, you can sort that out. But I mean, you are sort of lowering this tether down. How low could you go where sort of the kinds of electronics and the kinds of materials that you would want to make one of these, this tow body out of starts to be at risk?
Yeah, that's really what we're trying to understand in this NIAC and through various studies, understand, basically how low could we go? How low do scientists need to go or want to go? The key limitation seems to turn out to be power. Because in principle, you can run an active cooling system down as you even get close to the surface of Venus. But as you get below those clouds, solar power dissipates. Even though Venus is much closer to the sun than Earth, solar is not very efficient at those temperatures. And so you can run an active cooling system, but only for so long. That's why all of our concepts for Venus landers and the previous landers from the Russians didn't last very long on the surface. So the same is true for this tow body. And it's not going to go all the way to the, super extreme pressures and temperatures, but even at, let's say 45 kilometers, we're talking about around 100 C, right? So that's pretty hot. It's hotter than electronics typically want to go, and it's certainly hotter than an infrared imager wants to go, which likes to have a nice cool detector for good quality. So we are exploring the whole trade space of how to survive at different altitude bands, how long that might take, and essentially whether or not we can harvest energy from the wind that the tow body is experiencing through either a wind turbine or maybe even also using some solar panels to actively provide power for this cooling system. So the internal of this tow body can stay at nice, comfortable room temperature while the exterior is hotter and hotter. So we don't know where the threshold is there. The laws of physics don't necessarily preclude us from going lower. But actually, aside from power, the other key challenge is the wind drag. So the balloon will be sitting comfortably at whatever altitude it's at, 52 to 55 kilometers, something like that. And it's basically traveling with the prevailing winds at that altitude band. But we kind of know from prior missions that there's this wind shear profile in the atmosphere, not too dissimilar from Earth's atmosphere, so that balloon will be traveling at something like 200 kilometers an hour, 150 miles an hour. But that's different for every layer. So as we drop this thing lower and lower, it is seeing really strong winds with respect to the balloon. So it's basically being blown downwind. So the limit might actually turn out to be just the drag on these things, because what happens is as you lower something down, it blows downwind and you don't actually get that vertical penetration through the clouds that you would expect. So for example, if I bring a 10-kilometer tether and hang it on there, it's going to be 10 kilometers long, but it might only penetrate down 5 kilometers because it's blowing backwards because of this wind profile. And that's a phenomenon that's actually really hard to overcome, because even with very thin tethers, the drag is pretty extreme. So that could actually be the limiting factor on how deep we can go into the atmosphere.
Right. I'm kind of imagining like a boat that's sailing on the ocean, and they're putting a rope behind with knots on it, and they're sort of seeing how far the rope is sort of flowing behind them, and that allows them to calculate their speed. But in this case, like, we know that the winds can transport a balloon around the atmosphere of Venus in like 4 days, as you said, 200 kilometers. Like, it's fast. And yet I'm trying to get a sense of then how that wind, that shear at a lower level. Are you saying like the balloon is going to be going, say, east to west with the prevailing
largely
Venus version of the jet stream, but then the shear, you've got the winds going, say, perpendicular to it, or even in the same?
There is a north, south, east, west component. By and large, it is east and west. So what generally will happen is you're going to get slower winds at relative to the ground at these lower altitudes. And if you can think about it, like the tow body down there is going to be trying to stay at the local wind levels at that altitude. So it's going to be kind of trying to follow the ground more closely, whereas the balloon's being swept much faster in this higher altitude band. But it's funny you mentioned boats, because actually that's the domain where this tow body concept really sees a lot of application on Earth, because boats, not just for measuring speed, but just to deploy subsea vehicles down below where they can map the seafloor and do other sorts of measurements. They often deploy these tow bodies, which have the same set of challenges as Venus, or many similar challenges, where they have a cable and a body down there that's being dragged behind a boat. They're trying to get down while also being subject to this relative drift.
Yeah, I know, like sailboats, they'll deploy a sea anchor to try and slow themselves down if the wind is too strong. And so, but I like the idea that you've got this tow body down in the lower atmosphere. It's being kind of dragged along by the balloon that's trying to go faster, and then that is that's making a wind turbine on this tow body turn, and then that's generating electricity, and then using that electricity to run a cooling system.
Yeah.
And I guess simple, that's the question, right? Like that's the proposal.
That is the proposal. I mean, there's definitely different aspects to this, and we also the initial form of this concept actually didn't have any desire to harvest power. It might actually be difficult sometimes to rely on that wind shear because there are parts of the atmosphere that might not have that wind shear. So we also will have the ability to reel it back in, like a fishing reel, and dock with the gondola and recharge up there. So the initial concept was to have just full recharging of the onboard batteries on the tow body back at the gondola, because it's sitting up at a nice altitude where it can get good solar exposure for solar power, and then basically lowering it back down and reeling it back up.
I've got to assume you've considered putting electricity down the tether.
Yeah, and it's still in the trade, although the physics there get really hairy with how power transmits over basically copper wires over such a long distance. Typically, you need either thicker copper in your wires to get more current down there, or thicker insulation to crank up the voltage. And both of those increase the thickness of the tether, which exacerbate this drag problem. So there's sort of a runaway scaling effect, where if you try to put so much power down there, the tether gets too beefy and you can't actually reach the altitude you want. So we're likely not going to be going that route, though. The one component we might have in the tether, aside from just its strength to hold the thing up, is an optical fiber. Now, an optical fiber is very, very thin, or like, human hair kind of thickness, 200 microns. But they can first provide the communications link between the tow body and the gondola, which would then relay all that data to Earth. But they could, in principle, be used as a power delivery device. We're going to explore that as well. People have put power over fiber before, essentially using a beam dump at the bottom of the fiber to collect that optical energy. It's not the most efficient, but it is more at very long distances. If you want to still use a tiny little fiber, it is much better than.
Right. So the goal here is, I guess the whole point of the NIAC proposal is that you're going to try and do the math on these various things to figure out what are the right altitudes, what's the length of the tether. Do you have any concerns about the strength of the tether itself? If say solar power was no problem, like, is there a sort of, like, how long could that tether be?
Yeah, it's a good question. And yeah, there's lots of modern engineering materials, high strength fibers that are kind of on the table in the trade space, and also potential jacketing to protect that strength member from the sulfuric acid and UV exposure. It'll likely be very thin, like millimeter thin, just to overcome these drag laws. But the interesting thing, at least from our initial analysis, is that the tether strength mostly doesn't need to withstand the weight of the tow body. Your first intuition is, okay, you have this mass hanging on the bottom of a tether. You can do the calculation how strong it needs to be. But actually, because of this drag phenomenon, most of the strength in the tether is needed to overcome that downwind drift of the tow body. So it's actually going to be drifting more laterally than it is vertically. So there's like I said before, sort of this runaway challenge where you want a stronger tether to have, higher safety factors. But the thicker you make it, stronger you make it, the more drag is on the tether. And, so there's sort of this feedback loop. So yeah, one key component of this NIAC is going to be trying to find the sweet spot in the architecture for how the tether should look like from a strength perspective.
And so I guess in your perfect world, the balloon is able to maintain its altitude. It can run a tether that gets you below the cloud tops. You're running this tether. You're running this sort of module that's flying in the clouds, and it's taking all these observations and taking detailed resolution images of the ground. Give me a sense of, in the 1990s, NASA's Magellan spacecraft gave us our pretty much first and still only images of the surface of Venus. How much better could we get if you were at an altitude of 45 kilometers above the surface of Venus?
Yeah. It's a difference in both resolution and in kind. So Magellan used a radar imager. So radar really measures sort of the structure of the surface. The real key value that the scientists are looking for from a subcloud imager is the wavelength. So we want to do visible and near IR. And the reason those bands are important is because we'll be able to start to see not only reflected light off the surface, which is kind of how we perceive the world, but in that near IR, because Venus is so hot and has potential active volcanism, there's some evidence for that now, that IR band will allow us to see potential hotspots and actual composition of the surface. Because if we have a multi-band imager in the visible and in IR, we can now actually see what the composition of those lavas are. So it's much more interesting than just the nature of the orbital radar measurements that Magellan made. And by the way, most of this imaging will be done at night. The most interesting parts, because then we get much higher signal to noise from the emitted light. So in order to really isolate what is being emitted from the surface, we want to minimize reflected light. So we'll probably be doing most of the imaging at nighttime.
But I think of, say the Mars Reconnaissance Orbiter at Mars. It is, it's taking pictures of rovers from space. It could see your coffee table from space. And I think, I forget exactly, it's like 100 meters is the resolution of Magellan. Like, it's not great. How, are we thinking features as big as what Mars Reconnaissance Orbiter lets us see?
Yeah, we're thinking probably a little bit bigger, maybe around like 1 to 10 meters per pixel. But it would be a similar principle to an orbiting spacecraft where we have this, what's called a push broom sensor, where we're basically imaging a small row of pixels, and it just sweeps along the ground track as it moves across the sky. But yeah, so these clouds at this 4752 kilometer band, they put a limit on the visible resolution you can get from orbit. Even with the best camera you can imagine, just the nature of the scattering of the clouds, I think it puts the resolution in the visible spectrum to like 100 kilometers that you can't see. So if you ever seen, when you Google like a picture of Venus, sometimes you're fed the Magellan photo, which is like this nice radar. But if you were to fly over there and look at it, it's just this big like cloud covered ball in the visible spectrum. And so that's the real challenge for orbital imaging in the visible and IR.
Yeah, I mean, the only images that we have of the surface of Venus come from the Soviet Venera program, from the landing site where the rover was, melting.
Yeah,
that's it. The lander was melting. That's all you got. Screaming. Yeah.
So hopefully this could also be some sort of reconnaissance mission for subsequent landed assets, landers or rovers. There's other concepts for getting much lower in the atmosphere, or even like roving around on the surface. There's still some challenges in the technology space to get something to survive for a long period of time down there, but we don't really have necessarily a sense of where we might want to send these, which in the absence of this kind of reconnaissance data. Because there's other concepts. So the Venera the Vega balloons that the Russians sent in the 80s, I believe they had dropped sondes as well. So this is another concept for getting under the clouds, is just a single shot. Wherever you drop it, you just have a camera on there, and it basically looks at the surface all the way and it streams that data back all the way until it crashes on the surface. And those are fairly simple devices, but they only get you the one spot, right? So this is trying to basically take a drop sonde and extend that to like this global perspective.
I also think, like, with the Venera program, the way the Soviets learned about the conditions on Venus was to send spacecraft after spacecraft to their death. And wherever they failed, they made the spacecraft tougher in that aspect until finally one was able to make it down to the surface and survive for whatever, less than an hour. But with this system, you could kind of probe carefully and then reel your spacecraft back up and sort of see how it's doing, and then probe back again and get a much better sense of those conditions and which parts of your spacecraft or your lander are starting to fail without losing the whole thing.
Yeah, that's a great point. You could definitely take a very incremental approach to deploying this thing and getting more and more sporty while you're monitoring the health and status of both the balloon. So I should say this whole concept is meant as sort of an extension of like what would probably be the more primary mission, which is the gondola on the balloon itself, which would have a much higher payload capacity. We're talking like a couple hundred kilograms, whereas this tow body might be a few kilograms. So the primary thing is to keep that thing nice and healthy up there. And so it will also be altitude cycling to do its science. So while it's altitude cycling, also the tow body, just because it's physically coupled to the balloon, will also be naturally altitude cycling. So we can certainly start to gradually push the limit in terms of how far we think we can go as we monitor the conditions.
Now, a question I get a lot from my audience is there any way to collect a sample this way? Could you find the tallest mountain on Venus and then try to drop a tether down, grab a sample, and then get away with it before, in the 45 minutes or so? Do you think there's any way to do that?
It's a great question. And I don't want to speak, but I think there is another NIAC concept looking at sample return from Venus. I think Jeff Landis, I'm not sure who the PI is, but I believe there is a concept to do something like that. I'm not sure if it's sort of like a tether.
It was a previous
impactor.
year. It was a couple of years ago.
Was it?
Yeah.
Okay. But yeah, I haven't looked at basically you're thinking about like a penetrator that would basically be ballistically deployed, like not pick up a rock, but basically like collide, grab whatever thing it hits, and then using the tether to pull it back up.
Yeah, reel it back up. Yeah.
That's a really cool concept. You definitely have to be really careful how you design that tether, because it has to survive the whole profile of the Venus atmosphere. And like we said, the balloon's going at 200 kilometers per hour. So whenever it deploys this thing, it's going to have to yank it back pretty quickly. So that's a really interesting concept that we in our study here, we're going to be developing the equations that would allow us to answer that kind of thing too. So we could also look into that.
Now, there are a few spacecraft that are headed to Venus now. You've got Da Vinci, plus you've got Veritas, you've got Envision, as well as a potential private spacecraft that's going to go into the atmosphere. What would you be looking for? What kind of data would you be interested in to help you refine your proposal?
Yeah, it's really interesting. So yeah, Veritas, my understanding is primary instrument is going to be this very high detailed synthetic aperture radar. So it's going to do something like Magellan, where it takes radar images from orbit, but also using the synthetic aperture technology, which is more recent, to get much higher resolution. So that would help scientists target where we might want to deploy this aerobot or balloon system. So what features are interesting. The Da Vinci probe, and I'm not knowledgeable about all of the instruments that they're taking, but I know they have it's a Da Vinci orbiter and probe. So they'll be deploying a probe into the atmosphere of Venus, and that will collect a lot of atmospheric data, pressure, temperature, composition, wind speed profiles. That will really help give another very valuable data point to architect this tow body system, so that we have a better expectation of what the conditions will be like in the atmosphere itself.
I want to go back to the infrared view that you might get from the surface of Venus. And, as you said, compare that to the radar image that we get so far. We don't get to really see the colors of things, how well they're absorbing, emitting infrared radiation. So, from a kind of a geologist perspective, what are the kinds of features that we could see on the surface of Venus that would be most exciting if we actually could see those visible near infrared images?
Yeah, so Venus's surface is really, it's my understanding, characterized by just volcanic activity of all kinds. So there's very similar kinds of volcanic activity you see on Earth, and potential active volcanism. So what emitted light allows you to do is really get the composition of those lavas and those basalts, the ones that are more recent even, and the more historical ones, because emitted light really provides that signature of what the composition of the material is, if you have the right imaging spectral bands on your imager. And then, of course, if there's active heat being generated from the surface, that would be a very bright signature in a nighttime IR imager, or even a visible imager potentially. So yeah, actually seeing hotspots of where active volcanism might be today.
Yeah, I know there was like some hints in overlapping observations from Magellan where they could see maybe a new lava flow, or maybe some kind of landslide or something, or places where you've got some kind of volcanic uplift in a spot. But that stuff, I guess, would become instantly obvious when you're seeing it infrared. Oh, there's a hot flowing river of material in this region.
Right. Yeah, and a lot of it is really unknown. I mean, I don't want to. There are Venus scientists that have expectations, but my take is that we really don't know what we're going to see. And bringing an IR and invisible imager down below the clouds is our best shot at really like seeing what's really there in all these different wavelengths.
Okay, so what, this is a phase 1 NIAC grant. You are starting on this journey. You've got a bunch of ideas, a bunch of questions, a bunch of engineering that you're thinking about. What are you hoping to sort of, once you've done the work, completed the research, and you're putting your recommendations, what are you hoping that you will have, sort of what conclusion you will have come to?
Yeah, well, obviously it would be great if it turned out to be feasible from all the different angles we talked about, power, thermal, all the challenges, right? But feasibility is a sort of a spectrum, and it trades off like what you could do. So you asked the question before, how low could you go? So that's one example of I think of these phase 1s as sort of exploring what could be done with the concept, like understanding the boundaries of what the laws of physics allow you to do with the concept, and reconciling that with what the scientists are interested in from this concept as really a focusing mechanism for what to study after in like a phase 2 and beyond, where you really want to spend lots of energy investigating and really what this concept should look like. So I'm treating the phase 1 as a real exploration of the concept, really trying to, I have some ideas based on some initial analysis we've done, but it might turn out in the course of the study that, the system's much more capable in this way than we expected, or this is a real limitation we didn't expect here. So it'll be these phase 1s are always a real learning experience, but by the end of it, we're hoping to say, look, under these conditions, this concept is feasible. It could provide a really useful instrument in the toolbox of planetary science. And here's what we would study next in order to get this to flight ready.
Right. Yeah. Ben, what are you obsessed with right now?
I'm having trouble focusing my attention on any one thing, but I'm a roboticist, and as a roboticist in space robotics. So obviously it's very difficult to send human emissaries to explore all corners of the solar system. So I'm always thinking about the next interesting frontier. So Venus is one that I'm working on. I'm also involved quite heavily in Europa and Enceladus, and how to get to these oceans where there might be life swimming around. So maybe in another NIAC, I'll be looking into some kind of submarine for Europa and not a tow body for Venus.
Right. Yeah. I mean, I get so many questions about that. People wanting to understand the intricate ways that you would actually make it down to, through the ice on Europa or Enceladus, and actually be able to explore that region. And
I'd love to talk to you about that at any point.
Yeah. Well, but it's really interesting just how all the various pieces actually are kind of in place. That these melt probes are being tested in Greenland, that NASA is testing out underwater robots that can swim under the potentially under the ice and search around, and lots of ideas for this. Do you feel like all the pieces are there from a robotics perspective?
Yeah, I get the same sense as you. Like from the technology perspective, all the pieces are there. There's still a big hurdle to go in integrating all the pieces together. And then the big challenge for these concepts to go all the way to the ocean is you need to have nuclear power. So you have to have either an RTG or a reactor. And so that's a big political and programmatic hurdle to try and convince people that you want to take some of their precious plutonium and use it in a different moonshot kind of mission. But the technical components of there, like I agree with you, they're really pretty mature.
Yeah.
In fact, I'm going to Alaska in June to drill through a big ice cap in Alaska to get to a subglacial lake there.
With a melt probe?
Yeah, this is part of a NASA P-STAR program to basically test some robotic systems and understand how the science operations works as we would expect them to.
Right. And so, I mean, obviously you're not taking a chunk of plutonium with you. What do you do to heat the probe with, when you're there?
Yeah, all terrestrial ice melting probes use surface power. It's really the only way to do it. So we have different types of tethers that basically put high voltage electrical power down there, and there's different kinds of resistive and heat pumps in the probes themselves to transfer that to melt the ice. But basically all the power has to come from generators at the surface.
But back to earlier in our conversation, you can see that experience you have with the actual, like, the thickness of the tether, how hard it is to make your electrons behave over long distances.
Yeah,
That's
it's
really
interesting because our world is becoming more and more wireless in our consumer electronics, but I just time and time again come across the value of having tethers in different ways in planetary explorations, providing strength, a lifeline, communication, power, just so useful, but they're tricky to manage. So it does introduce a complication.
Yeah, when we built our house, our electrician was, we're a little bit we're out of the city and we're sort of on a more rural piece of land, and there's like where the transformer is at the end of our driveway, and the electrician was just obsessed about how far away we were from that transformer. And he was like super glad that we're less than 170 meters away from the road, because if we were more than that, then he was just like, everything just gets so more expensive. And so even when the builder was trying to figure out where to put the house, he was like, could we move it like a little closer, like just a couple of meters in the direction that keeps it without you needing to build a whole new transformer to keep the power going. And it just shows. And these just the cable that runs to my house is, I don't know, like as thick as your arm. Like it takes an excavator to lift the thing up and drag it along to move it in place. It was quite a thing. I didn't realize that's, and so when I sort of when I imagine the kind of tether that we required to pump power 10 kilometers through on Venus, I'm sort of envisioning this thing weighs, I don't know, thousands of kilograms. Like it's crazy.
Yeah. So, I mean, we're not taking the kind of hairdryer power that you have at your home or but
no.
But still it does add up to a lot. Even like a few millimeters, like this much is really intractable for Venus. Like even a one millimeter is kind of our target. If we start to grow beyond a millimeter, then our lives gets really difficult.
Yeah, really interesting. Well, thank you so much for taking the time to chat with me. Good luck with making the numbers work, and I look forward to a future balloon mission on Venus.
Yeah, great. Thanks for talking.
I hope you enjoyed that conversation with Ben Hockman. Now, I'm going to give you some additional resources, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew Gross, Bear Lake Roofing, David Gilton, David Matz, Dennis Alberti, Dustin Cable, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Robach, Sean Sargent, Spiderswap.io, Stephen Fowler Munley, and Vlad Chiplin, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. Now, if you're interested in the exploration of Venus and especially NIAC grounds, we've got a lot of really interesting interviews that have been coming out fairly recently that I think you're going to want to check out. Now, older interview that I did was about sort of more extreme temperature components, things that can actually handle being in the heat down at the surface of Venus. And so maybe that's a pathway to explore this. But then also the kinds of technologies that you would use to keep a balloon aloft for a long period of time. Think about how helium balloons tend to deflate over time. How could you keep inflating the balloon? And so I've got another NIAC award winner that is proposing how to fix that problem. So I've done a lot of really interesting interviews about the exploration of Venus, and I will put some of those links down in the show notes. All right, we will see you next time.